Hello. Today I'd like to talk to you a little bit about classification methods that use an ensemble approach. And it's an ensemble method such as commonly known as bagging and boosting. So what is it? The idea is to combine different approaches and algorithms. We do it because sometimes it does a better job. And so bagging is creating additional data by selecting with replacement items, and we'll talk about what that is in a minute. And I'm sure many of you remember. Boosting is running models in series and adjusting the weights based upon performance. So an ensemble is when things work together. That's literally what it means. Ensemble learning is a machine learning approach that uses multiple algorithms to ideally produce better outcomes. And the reason is we're trying to reduce the error associated with a particular type of model, so you may adjust it. And this is actually applicable outside of classification and machine learning, and is used in AI in general. A little bit of replacement or revision or revisiting of statistics with and without replacement. Whenever you pull a certain sample from a subset of a sample from a population, with replacement, you put them back at the end of the sampling. So you pull them out and then use them and then put them back, essentially, is how you can think of it. Without replacement, when you take them out, they're out. And so they can't be available in the subsequent sampling. So in here, you can see one is present in both of the samples. Bagging is a short form of bootstrap aggregation, essentially. So it's an ensemble technique that is going to divide a data set into n samples with replacement, and then each of the divided samples are then trained separately into a separate machine learning model using a different machine learning models. And then the output is combined together in some fashion, picking the better by using some sort of classification or something afterwards. To determine which is the better approach. Here's a lot of code, and I'm in front of some of the really important bit here, but it comes down to an example of how to do this, and this is taken from an O'Reilly text. Ensemble learning is part of the name, a great use, and it's basically all comes down to using this resample scikit-learn utility function. So to work our way through this code, and I'll corner so you can see what I'm talking about. Up here's the text that I was mentioning, and right down here is where, well, here's the best approach. I'll just pop off the picture for a moment, leaving a bit of a sideways ghost. Fun. All right, so we have in samples is set to 100. We do a make classification, and that's going to go through and basically using the samples, the features, and so on, various named parameters, and that's an example of Python's named parameters. We then do a test train split, separating into looks like 10% and 90%, seeding it with a random seed, and then basically work our way through the rest of this. And so at the end of it, it's using a series of decision trees to figure out which one of them is doing the best, and then essentially using the decision trees as a means of doing classification. And the overall accuracy turns out to be pretty good when we use this approach. So the idea here is that you want to improve the performance of your overall model. And instead of giving equal weight to all of the classifiers, you weight it according to how well they're doing. So you essentially adjust the weights and rerun if it's incorrect. So this is a simplistic form of fitting that you'll see in a much more complex form in neural networks. So when you adjust the weights, you want to stop at some point, or you may overfit it, what we're getting at here in the long run. So you're basically adjusting the weights to some point. If you do it for too much, and in this case, we're using a majority voter approach of the various models. So that means each of those models inside of that ensemble have a vote as to what something is as far as classification goes. And so the majority wins is the basic approach. Here's a Ada Boost example, a lot shorter code because we're using a higher level function. So we're giving it, we're loading the iris data set in here. And then you're basically saying use the Ada Boost classifier with 100 estimators, and then calculate the accuracy score, and it comes out at about 95%, which is really impressive against iris, because there's a certain amount of it that's pretty challenging to do. So again, the idea of this whole concept is using multiple things together, and then figuring out a way to determine what the outcome is amongst them. So some sort of a quorum or majority rule sort of approach. Gradient boosting is similar. It's iteratively increasing the weak learners, right? So basically, when you add the new learners after increasing the weight of a badly classified observation, in gradient boosting, you train a new model on the residual errors instead, right? So that you're making prediction based upon the residual areas. And so what you're basically doing with things like a gradient boosting is you're trying to hone in on a minimum or maximum. So you're adjusting somewhat intelligently, so you're getting to where you fit better. Ideally, in this case, it didn't do quite as well as the previous examples. XGBoost is another common one you'll see, state-of-the-art algorithm, right? So generally, XGBoost is going to be the algorithm. One of the things you will likely want to consider if you're looking at ML and classification and so on is AutoML. Using AutoML inside of environments like Databricks or Azure's AutoML facilities may result in much better outcomes. Thanks for watching. Stay tuned.